A very short presentation about my research activities inside the Polytechnic di Milano Department of Mechanical. My name is Andrew Manes, as you can see. I will present two activities. This is a work in progress, and so there are not definitive results. The working is focused on experimental tests on complex mechanical and aerospace components. In particular, two types of experiment: a fatigue and damage tolerant experiment on a full-scale main rotor hub of a real helicopter, and a ballistic impact test on tubes that simulated the transmission power shaft of the rear rotor hub of an existing helicopter. For our concern, the test on the main rotor hub, it is a titanium component. Inside the titanium there is a filament graphic winding, circular, that is glued inside the titanium. And this is used as a fail-safe device in case that the titanium breaks. In particular, in this test we have simulated the contingent load applied on the rotor hub, and we have used 15 hydraulic aerodynamic actuator and a very complex system to control this actuator in order to apply the load in the real phase used during the exercise of the component. The test, that is a very long test, you can see the start the 6th of June of 2007 and the 1st of April, it's not a joke, of 2008. The test consists in three phases. In the first phase, the safe live, an amplified start-stop spectrum is applied to the component in order to nucleate and propagate the crack inside the wall section of the titanium part. In the second phase, the damage tolerant behavior of the component is analyzed, applying five times 3 package of load spectra, a start-stop and ground and high frequency spectra. These are acquisition from the load. In this case, the aim of the damage tolerant phase is to simulate 2,500 flying hours of the component in order to verify that the component is able to carry the helicopter in a safe fly, also in case of the whole titanium section is breaking. And then finally a start test to verify the ultimate load of the component. In this case, you can see in these photos you can see the complete failure of the titanium section in the first phase after about 60,000, 62,000 cycles. The failure, the crack involved the whole C section of the hub. Little film about the second phase of the test. This is the damage tolerant test. This is the crack tip. It's not a propagation. The propagation was in the first phase. In the first phase, in a very few cycles, the crack propagated until the whole section. Consider that the material of the hub is titanium. That is very good in this case. Let's try again. Jump the slide. Alright. During the test, one of the most important activity was to acquire the most of the data possible. So strain gauge to acquire the strain along the titanium section, and laser measurement to acquire the displacement of the crack tip, both horizontal and both vertical. Of course, because the next step is to simulate this component using finite element method, and so this is very useful to validate the model. The next step, as I just said, is the simulation with a complex finite element method, finite element model that is very complex as far as the geometry that is representative of the component, for the material, because inside there is also the circular winding, there is also the glue is modeled, the glue that connects the winding to the titanium section, and it is very, very important, the modeling of the glue and the correct constraint and correct loads. This is the most stressed zone, and of course this is the point in which the crack started. The first activity that we made was a classical fatigue approach in order to estimate the fatigue life of the component using the state of the stress inside the component in the most stressed zone. This is the principal stress, and the material data in literature. As you can see, the stress in the most stressed zone is like monoaxial stress, and most important is in phase. And so using a classical approach in fatigue is possible to use, for example, a simple approach like sines, or for instance also a simple monoaxial approach. For Aconset, the material data, a very large research in literature has been made, because there are a lot of data on this type of titanium. And in this graph you can see our prevision. These points are our prevision with the range of the prevision, and this is the effective breaking of the component. Consider that the component is very, very complex. So the results are very, very good. The second step is to simulate the propagation of the crack. This is more capital in progress. We have first results that are very good, but are not definitive. We are using both Abacus and Frank 3D, that is a software dedicated to crack propagation. It is not a finite element software, but is a boundary element software. The second activity that I want to show is a ballistic impact experimental test for simulate the impact behavior of the real transmission shaft of a hub. In this case, you see the complete test rig. There is a precision gun, there is an infrared sensor to measure the velocity after the gun. There is our objective, and there is a true catching plate that we use to acquire the velocity and the direction of the projectile after the impact. Also, in this case, the aim is to obtain the more possible data to compare with the finite element simulation. You can see the gun. The gun is a very precise gun. It's not a handly gun. There is control for pitch and for yaw. There is the possibility to repeat the shot always in the same point. That is important needing for this test. And this is the bullet. This is the classical 7.62 caliber gun. This is the instrumentation inside the test facilities. You can see the tube, with the constraint of the tube that is very useful because allows to put the tube in the correct angle against the bullets, and then there is the catching plate and the infrared measurement system device. These are the catching plate. You can see, for instance, the hole of the bullets in case that no tubes are present, and the hole of tubes when the tubes are present, so the projectile have a little turn. In the two frames there are two accelerometer connected with a high-speed measurement system that allow to acquire also the velocity after the impact. You can see right. You can see the impact over the tubes. The need is to obtain a 45 degrees impact, because consider that the tube are power transmission, so are subjected to torsion, and to obtain a single hole, single damage, or a dual damage, to evaluate the more dangerous damage. The next step, but it is a work in progress, starting from the finite element simulation performed by Dr. Colombo. The test is to acquire the damage using a three-dimensional optical scansion, to acquire the residual stress around the hole, and to perform final test on a triaxial testing machine in order to apply tensile but expansion of torsion on the component, and to evaluate the effective behavior and damage tolerant behavior of the component.